what I like to do today is to provide an overview of our simulation products, on which we have many. So this is my agenda. So we're going to look at the role of simulation in digital prototyping, our portfolio. Then we'll be looking at some individual products like Nastran In-CAD, Simulation Mechanical, and some CFD, just to give you a bit more background, and we discuss sort of licensing options too. So simulation is often an area that's neglected in the design to manufacture process. You may design and engineer the part, then it's manufactured, and there may be physical validation, physical testing going on to see if it will perform and work and can be manufactured. Simulation will allow you to test your designs, test that the parts can be manufactured without any issues before committing to the final design, before cutting metal, before producing anything. So it will reduce the reliance on physical testing, which can be very time consuming. It allows you to look at different designs, be very creative. Many companies are growing through innovation, and it allows you to avoid the risk of coming up with complicated designs or new designs that you're not sure of. Typically you may over-design just to be safe. So simulation lets you try out different options and compare designs very quickly. So where can simulation tools be used? Well, they can be used in automotive, energy, buildings, industrial plants, industrial machinery. Anywhere there's a need to check the performance of a design, to check that it will meet design criteria, various specifications. It gives you an insight to performance levels of the designs, where you can optimize, save material, where you can improve the design of the component. So just to give you some background on Autodesk simulation, Autodesk have been very active in acquiring companies and technologies since 2005, having spent $900 million plus on acquiring such technologies. So my background is actually from Moldflow acquisition in 2009, that's plastics injection molding simulation. Since acquired companies like Algor, which is now a simulation mechanical product. We have CFD, composites, and NEI software is the Nastran code that was recently acquired 2 years ago. So this gives us a comprehensive portfolio of simulation products. So for structural mechanics, we have a variety of products there, which I'll come on to in a moment. We have CFD for flow and thermal analysis. We have structural analysis with our robot product, looking at large buildings typically made from steels and concretes. It does code checking for all the countries around the world. If you're looking at plastics, then we have Moldflow technology to predict how they will be manufactured and the quality of these parts. Also have composites analysis. So many of these materials, these could be layers of ply, and in each ply could be continuous fiber in different directions. And these are quickly replacing metals in many areas because they're lighter and stronger. They've become very popular in the automotive industry. So this software will show you how they will perform and how they will fail. So on the mechanical, the finite element analysis offerings, we have a few products. The two of them I'm going to focus on to start with. One is Nastran In-CAD, which is embedded in Inventor and SolidWorks, and the other one is Simulation Mechanical, which can be standalone but still launched from products like Inventor. We also have Autodesk Nastran, which requires a third-party pre- and post-processor like HyperMesh or FEMAP. So the Nastran solvers within these products are very accurate. They're tried and trusted. They've been verified with the standards agency with over 5,000 tests validated per release. It is industry trusted. Markets that use Nastran, aerospace, automotive, government and defence, marine, ground vehicles. So this is software that was developed by NASA in the 60s. The code became public, and the code that we acquired was NEI Nastran, which is very accurate, very robust, very efficient, very fast. And the key developer of this code is working within Autodesk now with our development team. We have many Nastran experts within Autodesk. So the Nastran In-CAD product is CAD embedded. You'll see this inside Inventor and SolidWorks. If you have a license of Nastran In-CAD, it is networked. Even if you have one machine with Inventor on, another machine with SolidWorks on, Nastran In-CAD can still be shared between these machines. It allows you to stay in the environment of your CAD system without coming out. So you can quickly perform checks on your designs to see if they will perform under different working conditions, and helps you to optimize the design before you finalize. It allows you to do checking up front rather than give this to an agency or a high-end analyst at the end of the line, which all sort of delays project time. So if you're familiar with products like Inventor simulation, that's very limited in that it can only do linear statics and modal frequency. So linear statics will allow you to apply a load, assumes the stiffness is constant, gives you deflections, stresses and strains. This can be very useful in a lot of cases. The natural frequency analysis will show you the frequency that your part will start to vibrate at and the shape that it will go into. With Nastran In-CAD, you can do that, but you've got access to much more analysis capabilities, all in the same environment. So it can show you what multiple of a load, you can buckle your part, you can do thermal analysis, steady state, or thermal loads, temperatures changing with time. It allows you to define the composition of your thickness. You have different materials going through it. There may be contact situations, parts moving. A non-linear analysis. This is where the stiffness can change or the material may become non-linear and permanently deform. You can apply vibrations to your designs to see how they will respond. Some companies have to do this as part of a specification and normally do this with physical testing. You can look at hyperelastic materials like rubbers. You can do drop testing. So it's very comprehensive. No additional licenses or modules are required. They're all included in the Nastran In-CAD product. So, for example, if we were putting a load on this stool and we ran a basic linear static analysis, it's going to predict about 193 millimeters of deflection. With stresses very high, showing that it's going to foul. And this is because, if you look at the graph on the left, that stress against strain or load against deflection, it applies all the load in one go, measures the deflection, the slope of the stiffness, and it assumes the stiffness remains constant. But in reality, the stiffness may change as the load is being applied, and you may get a stiffening response, as you see on the graph on the right. So you may actually get lower deflection. If it softens, you may actually get larger deflection. So non-linear analysis will apply the loads in smaller steps and allow the stiffness to change for much more accurate results. This is very important if you're dealing with components which have a large surface area to thickness ratio, such as you may have with metal sheeting, for example. I'm just going to give you just a quick insight to the Nastran In-CAD. So we're inside Inventor here. We're not going to actually analyze this whole assembly. This is a packaging machine, but this sort of can show you our approach to how we would handle this. So with this machine, you may be interested in looking how it performs, making some modifications. So at the far end is where cups are lifted via vacuum, and underneath there's nests which will raise the cups through a rack and pinion system. Now this may have been tested physically and shown to be okay, the machine's working fine, but now they're looking to increase the capacity of how many cups can be handled in this machine. So the arms that support the nest, that support the cups, we're actually going to make these longer. So in your CAD environment, you can quickly do this. You can make the design change, make these arms longer. The idea is we're going to be able to sort of handle more cups. The design's been updated, but will it work? Will there be any problems? So this is where you can take a sub-assembly. We're looking at the C channel and the arms that support the cups. And if you have Autodesk Nastran In-CAD installed, there will be a Nastran tab. It takes you into the Nastran project tree. You can choose your analysis type. All the different analysis that I explained before are shown here. And you can choose the analysis that's relevant. We can assign materials to different components. They can be imported from the CAD system, or they can be chosen from the libraries that are in there. We can apply a type of mesh. It could be a shell mesh or a solid mesh. You can have a mixture of both. The meshing is very fast. We can apply constraints just to represent how it's being held in the machine, so we don't have to model all the components attached to this sub-assembly. So we're working directly from the CAD model, which many systems can't do. You almost have to create a new model if you're working in some other products. We can say that the arms are bonded to the C channel without having to model the bolts either as well. So we haven't added the mass of the components on the arms, but we can apply a concentrated mass to represent the loads on them, which will save again much modelling time, meshing time if we want to include all the other components. So we can run like vibration analysis to see how it's vibrating. And obviously as we made the arms longer, the design is going to be more flexible. So what we can do, we can simulate how the machine operates. We can apply like a velocity to the end of the C channel to represent its upward movement. And we can also define that it comes to a stop after a certain time. So we can define these load steps. We can check this visually to see what we're getting. So this C channel is going to be moving up with the arms, and then it's suddenly going to stop. So we can run the analysis with these conditions, which will only take about 2 minutes. We can choose to select time steps. We're going to have time steps 0.003 seconds, recorded every or 50 times. So when we run the analysis, we can page through all these time steps. It will animate through them. We can look at things like stresses, we can look at displacement. We're looking at the stresses here as it's operating. We can see the arms are moving. We can actually interrogate this a bit more. I've taken points or nodes at the end of the arms and viewing them graphically. Now the units that will be shown is in inches, but this is showing that as the arms go up, they actually deflect back down again by about 3 millimeters, which is excessive. So the cuts are likely to fall off. So this design isn't really optimum at the moment. So we can make it a bit stiffer by increasing the thickness of these arms, we can just increase the thickness of the mesh to see if it works, and rerun the analysis. We will see that the deflections are now less than 1 millimeter, so this design is much better. So while staying in the CAD environment, we can come to a final design, we can finalize the design of this component, update it in Inventor, it will update our assembly. So we now know that this will work. This is something the CAD engineers can do at the design stage. So we've got customers using this all over the world. One such company is TE Connectivity, making sensor solutions. They're really interested in non-linear behavior. They're actually SolidWorks users. Many of the Nastran In-CAD customers are using SolidWorks. And their main challenge was getting products to market on time. They needed more upfront analysis to optimize the designs. Another example is GT Engineering. They're happy to use basic linear analysis, but for their industry they really wanted an engineering solution that was an industry recognized product. They have to submit reports, have to be accepted, and as soon as Nastran is mentioned, then they know it's tried and trusted software. So simulation mechanical has many capabilities, very similar to Nastran In-CAD, but this can be standalone, it can be networked also, and it can import files from many different CAD systems. You can actually launch it from within Inventor or SolidWorks if you have a license of simulation mechanical too. So once again, it's being used in all industries: structural, electrostatics, drop testing, automotive valves, and it's got many capabilities too. So it can do fatigue, buckling, applied vibrations, thermal, non-linear, motion, impact testing, drop testing. Very comprehensive. You can read in large assemblies. You can easily create a mid-plane mesh, or you can use solid meshes. You can suppress areas or parts you don't want to use in the tree. So it has a very easy to use interface. It can perform pressure testing. So many of the customers use this for looking at the performance of designs under pressure. It could be internal or external. The results here are being exaggerated, the deflection, just to visualize which direction areas are moving. You can take slice planes. You can look at deflections, variety of stresses like von Mises principal stresses and strains. It will produce membrane and bending stresses, the stress linearization through thickness if you have to work with certain codes like DNV. And it also has a automatic pressure vessel builder to make solid or shell structures, flanges or nozzles. It's very fast and very efficient. You can do non-linear as well, so like Nastran In-CAD, you can look at permanent deformation. So this is a slice of a steel ball hitting this girder. The bottom graph on the right is showing the position of a point on top of the girder. It deflects downwards but never recovers back to its original position. It can perform motion analysis, so it can take into account direction and time. You can define which surfaces are in contact with one another. There's friction involved. As things are moving, you can see stresses and deflections. You can prescribe the actual movement in an event setup. Very easy to do. If you have Inventor, you can do parametric design studies. So in this case, we're within Simulation Mechanical, we may want to see the effects of changing the large radius and the small radius on results like weight, stress and deflection. So it can run with a combination of these changing radii and show you the results. So within Simulation Mechanical, you can see your inventor design parameters. You can select the ones of interest, like large radius or small radius at the bottom. You can put a range in which they can vary, going from 25 to 37 millimeters, and 9 to 13 millimeters at 3 levels. And it will quickly run all those combinations of radii. And it will report the stresses, weight and displacement for each configuration. And you can put in an upper and lower limit, and it will show you which configurations meet those limits. And if you click on the index number, it shows you the results. So this is the same machine that we saw before. We're now using Simulation Mechanical to look at a different aspect. We're going to look more in the middle section where there's some forces being applied to some equipment. We're going to look at the performance of some of these items. Just having a couple of issues running animations over the web at the moment, so just get that working. Okay, what I'll do, I'll just play it here, perhaps. Hopefully you can still see this. So we're in Inventor at the moment, and we've got this large machine. We can select areas of interest from the assembly and put this into Simulation Mechanical. So this is an assembly that we're looking at, which takes a load. And there'll be a simulation tab in your Inventor or SolidWorks product, which allows you to launch this into Simulation Mechanical, or we can open Simulation Mechanical and import files from different CAD systems, including Inventor. We can apply a force, where the force is being loaded. We can apply constraints, and we can look at stresses and deflections. In this particular case, it's showing that the stresses are very low. But what happens if this loading is continuous, it's cyclic, then there could be a risk of failure through fatigue. So there's a fatigue visit which allows you to step through very easily. You can choose fatigue graphs for different materials. We can actually define the loading. We can say that this loading is going on and off for each cycle. We may have a desired cycle life of 1 million. It will quickly run, and it's reporting that the life cycle is just over 1 million. So it's very close to failing before the required life cycle. We can quickly view areas where the highest damage is occurring. We can then modify the structure in this case, the support, to make it increase its size, just to make it a bit stronger. And we can rerun the analysis. So we can quickly launch the analysis, rerun the fatigue, and we now get results of virtually infinite life, just for that one design modification. So we know that it's going to perform for the expected life of the machine. You can actually plot the desired life cycle or the expected life cycles on the component. So there are many customers using these products. Bells of Pacific, they make products to transport materials. They don't want to be making physical prototypes to see if they work, so they're doing this with simulation up front, make sure they do, and they're optimising design as well, seeing where they can take out material to keep costs low. This is Swiss Federal Railways, who had an issue with birds being electrocuted on their power lines. So they designed a plastic cover to cover these power lines, but this plastic cover has to be removed for maintenance purposes. So they pull this device through, which opens up the cover for removal. And they use simulation mechanical to see if this idea would work, to see if it would open up enough to be removed, to see what stresses are induced, make sure it wouldn't break, and also it tells you what force is required to pull this device through. So we also have Simulation CFD, which looks at fluid flow, thermal analysis too, looking at heat transfer, motion. It's a very easy to use product, works very well with CAD, and it can be used as a virtual test rig. So it can be used for wind tunnel simulations, looking at buildings, looking at thermal behaviour of equipment. You can look at flow through valves, pumps. It can be used to look at the factory layout too. So if you're involved in flow control designs, you can look at aspects that are important to you, like flow rate, pressure drop, if you're getting turbulence, recirculation, cavitation, erosion of your designs. So cavitation is a big problem. This is where you may get negative pressure. Fluid may, or water for example, may turn to steam, may turn to vapour. This can be very corrosive. So it predicts if this is going to happen and where it will happen. It will show you erosion results too, which can also be related to the life of your product. So in your CAD environment, you may have a design. This is a valve, and we're looking at different designs of valves to see which may work the best. Without simulation, you may just go with the first design, your first idea, but not really being able to check out other ideas at the design stage. So in this case, we're looking at different designs. So one of the designs has a cage with 4 slots around the poppet. Another design has 24 slots. And there's a third design as well, in which the slots are varied in size from one size to the others. That's what we call staggered slots. If you run CFD, it allows you to look at the velocity of the fluid going through the valve, through the cage and poppet area, and the direction. It can show you areas of recirculation where these areas aren't being very effective. You've got redundant flow effectively. You can also look at pressure drop. What sort of pressure drop are we getting from one end of the system to the other? And this can be very powerful. You can take results at any point in your model to track things like temperature, velocity, pressure. So this is the equivalent to having lots and lots of sensors in your designs, thermocouples, to measure values which we'd normally try and do through physical testing. So this can really replace physical testing, really cut down on development time to get the products right. There's various ways of looking at results. You can look at it through slice planes or ISO surfaces to show you which areas of the fluid are moving the fastest or slowest. So you may have looked at, if you analyse the 3 designs, there is a design study environment, a decision centre, in which we can quickly compare the results. So we're looking at different results from using 4 slots in the cage, to 24 slots, to staggered slots. We're looking at pressure distribution here. So on the original design, we're getting very large pressure offset on the end of the poppet. and this can cause vibration and chatter and noise. As we go through the different designs, the pressure magnitude reduces, the variation reduces, and this is quite significant in reducing vibration and noise. So why are we getting this improvement? Well, we can take a cross-section. With the original design, this is the velocity and the direction, and we see that the direction of the fluid is very irregular. We've got some recirculation, not streamlined. As we go to 24 slots, the flow is becoming more streamlined, and as we go to the staggered slots, it's nice and smooth. We're actually getting more efficient flow going through as we go through the design. Now, when we're in the CAD system, you can quickly launch from your CAD system into CFD just by selecting the tab. And then if we make a design modification, that will come through as well, and it will use the materials, the mesh, the conditions that have already been set up for your first analysis on your first design. You can also check things like effects on pressure drop through the different designs. So although we've made the flow more efficient, have we affected the pressure drop? And we see that with the third design on the right, the pressure drop is actually lower. So not only have we improved the flow, but we reduced the pressure drop, which means a higher output for a given flow rate. So this is a company that were making pumps over 1 meter in diameter, and they weren't really able to test these by simulation previously. They were physically testing them, so they were over-designing. And with Simulation CFD, they're able to optimize the designs up front. And this water pump, just by changing the angle of the vanes, improves the flow rate through it without increasing the pressure loss. So they're able to increase the efficiency and flow rate by 11%. And they can do this very quickly by comparing different designs at the simulation stage. So this software can be very advanced. You can look at free surface area flow. So this is the boundary of fluid and air, fluid and gas. And you can look at the effects of designs on preventing sloshing, as we're seeing here. So with regards to facilities management, just looking at the ventilation with CFD can be very significant in reducing operating costs. So there was this large layout. We were looking at different designs of ventilation, and just by modifying the ventilation, the ducts, they're able to control the temperatures very well. They were saving about $83,000 just on the ventilation costs. But this plant also houses machines, and when the temperature varies, it affects the production. So there are additional savings in machine downtime and scrap that was created as a result of the temperature variation effect on the machines. It can also be used to look at buildings, airflow around buildings, look at wind velocities which can affect pedestrian safety. This can also be used internally, so it can be used to show thermal comfort within buildings. It shows you the temperature distribution inside buildings, where your hot and cold spots may be. Again, that could be affected by your ventilation. So with CFD may predict forces on walls, either internally or externally, by applying CFD flow simulation. And these forces can be directly input into products like Simulation Mechanical, so we can actually see deflections and stresses as a result of these forces predicted from CFD. It's the same with thermal. CFD can show temperature changes, perhaps as fluid is moving through a system. It could be hot, coming in hot and cooling off as it goes through. And these thermal changes again can go into simulation mechanical for predictions of stresses and deflections. So if you're into Moldflow analysis, well, I certainly recommend this if you're looking at plastic part design. So many parts being made from plastic. You find plastic parts in all industries, and this can often delay a project if they're not right. So Moldflow allows you to look at the manufacturability of these and predict the final product quality. So will there be cracks? Will there be deformation? Will there be surface defects? So Moldflow helps you predict this up front. And one of the challenges is actually, can we fill the part? If you're making the part too thin, for example, or in a certain material, it can actually be filled. And what you don't want is to end up with plastic parts that cannot be produced to the quality desired, and they hold up the project. So we see a lot of designs going from metal to plastic. The designs are copied, which isn't good for plastics because you end up with lots of thick sections in plastics, which plastic doesn't like. So Moldflow will help you look at new designs, often going thinner, can make the part easier to mold and make it stronger. And to test its strength, we can actually take Moldflow results and put them into structural programs like Simulation Mechanical, ANSYS or Abacus. We have a non-linear link with Abacus and ANSYS as well for even more accuracy. So what we're passing on are the stresses from moulding. So plastic parts have internal stresses. Also material property changes due to the moulding process, due to the orientation change of the molecules, and particularly if it's fibre filled for reinforcement, then the fibre orientation has a large effect on its mechanical properties. It could be stronger in some areas and weaker in the others. Otherwise, structural analysis programs will assume constant material properties and no stress in the part. So we're offering perpetual licenses with our simulation tools, or you could run them on the cloud. So we have products based on Simulation Flex, which allows you to perhaps run one job at a time on your machine, or you can send multiple jobs to the cloud, and it will return the results to you. And this can be very fast way of setting up lots of analysis. You'll run in parallel, and the results will come back to you for viewing. We use Amazon servers. It's very safe and secure, and probably more secure than in-house computers, which can be hacked externally. So in our offerings, we're offering Flex licenses for Simulation Mechanical, CFD, and Moldflow. The Flex license is a 1-year license, and it does come with tokens that you're using in the cloud. The perpetual license, these can be networked, you own the software, and you can pay annual subscriptions for support and updates. The Flex licenses include advanced subscription. So typically you may have a design and then throw it over the wall for someone else to look at. You may be using external agencies, analysts at the end of the line. They can become a bottleneck. They've got lots of work to do. If the design isn't good, it comes back to you, and then it's trial and error, perhaps to change something to see if you can improve it. And then the process starts all over again. And this is actually from a company that were finding this process too long. So with the simulation tools up front, you can do many iterations of designs at the design stage, also within your design environment. Try out different ideas, compare designs before you submit a final design, which the specialist analysts can still analyze if required. But it does reduce product development time, it does take away a lot of the risk, it does allow you to be more creative. Okay, so I'm going to open it up for questions. Hope you found that useful. So I unmuted you, so are there any questions at all? from anybody? My name is Eric Henry, so my email address is there. So if you think of questions afterwards, you can always send me an email. We have a lot of information on our Autodesk website. You can look up simulation there. There's an address specifically for Nastran In-CAD. Show you more demonstrations of that product. We have a Sim Hub site as well, which gives you access to little TV sessions for different products and different applications. So I can't see if there's any questions that have been entered. Can't see any questions at this stage. So thank you for attending. I hope you found that useful. Gives you a better idea of what simulation products, capabilities Autodesk have, and the benefits you can get from them. Okay, so thanks once again, and enjoy the rest of your day. Thank you. Bye.